Ginés Carrascal. Hi, Ginés is computational scientist and architect on IBM Quantum, and he will talk about new trends in quantum machine learning. So, Ginés, the floor is yours.
To participate. Oh, okay. Yep. And really, I want to go some technical today. So we are going to see how to program quantum computers, and also I want you to understand this technology and maybe demystify a bit about this. So let me share my screen. And okay. This is just a picture of a real quantum computer, because many times people say, okay, but these things exist. And yes, quantum computers exist. And we have been working for some years using and developing quantum computers and searching for this utility of the quantum computing. And as you have been talking just a moment ago, the idea of offering quantum computing as a service is something that we have in IBM from the beginning. So we have been offering quantum computing in the cloud in the same sense as supercomputing is offered, like queues and jobs that you can run remotely in a big system. And also we think in this idea of the quantum-centric supercomputing, where we will get these data centers with quantum computing and classical computing capabilities, so we can really extract the most from both worlds to solve problems. Okay. So thinking about what we have with quantum computers, we have published this roadmap that we have fulfilled to the moment. And there are two significant points in this development of quantum computers, and is related to the capability of things that we can do with the quantum computers. And one thing that we are really working on is that we have created bigger enough quantum computers and good enough quantum computers. So we are entering in what we call the utility era. That is not already an advantage, is just that we are in the limit where we can start working with quantum computers with real size problems. So and we are trying to experiment in these real or near real size problems. And to really get the full capability of the quantum computing, we will need error correction. Okay, one of the problems of the quantum systems is that looking at this uncertainty principle, when you look at a qubit, you get the information or get some information of the qubit, but you destroy the qubit in the process. So you cannot copy quantum information. You can move it, but you cannot copy quantum information. And that is really important, because in classical computers, we copy a lot of times the information, and that's why we can make error correction easily. But in quantum computers, we need to make things in another way. So we will need bigger computers and more accurate computers to be able to create this error correction. And this is what we call the fault tolerant quantum computers. And we will be able to run really or to solve really big problems with this kind of computers. And this is something that we see at the end of this decade. Okay. And what we see in the process is that during these next 5 years, we are getting better and better computers that will be able to make things that maybe are not exponentially big, but maybe can add value to real problems. So that's why we really believe that this is the moment to start learning about quantum computing. And what I want to do today is bring you near the quantum computing and see what can we do around quantum computing and machine learning. In this case, that is my field of specialty, and give you the idea that you are able to program quantum computers, and this is more easy that it seems to be. Okay. In IBM, we have this quantum.ibm.com where you have access to systems that are online and accessible through the web. And this is the demo effect loading. Okay. So we have different computers of different sizes, but we think that really for utility scale problems, we need more than 100 qubits to be able to really make big enough circuits to solve interesting problems. So that's why we have removed all the smaller computers, and we are changing and creating new bigger computers in the cloud. So as I said, you have free access for 10 minutes of quantum computation time at a month. So you can start testing with these computers. And we have also some learning platforms, so you can also get some resources there. And what do we use to program quantum computers? We use Qiskit, and Qiskit is a Python framework because for many data applications, people are used to work with Python. So we find it interesting to develop the connections to the quantum computers using Python. Do quantum computers run Python? No. Quantum computers run quantum circuits, but we use a Python library to interact with the quantum computers, to send the programs, to get the results and post-process this. So let's see this in action. And I said I am I am going to show some amount of code here, but just for you to see that this is real, you can create quantum programs in an easy way. Okay, hopefully I can get to it. So for a quantum computer, we work with a quantum circuit. Okay, what is a quantum circuit? A quantum circuit is the unit of calculation. Okay, the qubits are the unit of information. The circuit is, yes.
Mean a little bit the notebook. Yes, Control Plus. Yeah, that's fantastic. Thank you. Yes, thank you.
It's more okay. Yeah. So the quantum circuit is something composed of some amount of qubits and some classical bits, because what we get out of the quantum computer are classical bits. We cannot see the states of the bits. We read zeros and we read ones. So we need, in this case, I make here a system with 3 qubits inside and only 2 classical bits that I'm going to read, okay? So initially, our quantum system is in an state that we represent like a vector, okay? So quantum computing is somehow a lot of geometry inside. No, in classical computer we make a lot of calculus. In quantum we make more algebra, more geometric calculations. So we represent the state of a system like a vector with a lot of components. You will see that the number of dimensions of the quantum space is 2 to the number of qubits. So in classical computers, we have 2 to the number of bits numbers, but we have in a quantum computer 2 to the number of qubits dimensions. So we have a space with a lot of dimensions. And we represent, for example, in a system with 3 qubits, we represent the state like something related with the probability of measuring 0, 0, 0, 0, 0, 1, 0, 1, 0, until 1, 1, 1. So these are the different possible measurements of this system as probabilities, okay? This really, the probability is the square of this number, but because this is a complex number and we have more properties inside. And what we can do with quantum computers, we can make superposition. And superposition is, as you said, I haven't showed this, a quantum circuit that we can print like ASCII or draw more beautiful drawings is something similar to a music pentagram where we have the qubits that always start in 0 state, and we apply gates that are in IBM case are microwave pulses, but are something we send to the qubits to make some actions to create changes. And in this case, if we use this gate that we call Hadamard gate, we can put this qubit in a superposition state. That means that we have a probability. We have the probability is the square of this, so is 1/2 probability of looking 0 and 1/2 probability of getting 1 when we measure. So in this state, all the other qubits are zeros, and we have half probability measuring 0, 0, 0, half probability measuring 0, 0, 1. Okay? We usually make a graphic representation of this using log sphere, and you have to be careful with this because this is a representation of individual qubits. When we have qubits that have no interact between them, we can draw a sphere where we said that in the top is the 0, the bottom is the 1, and this vector represents the probability of being 0 or being 1. In this case, this qubit has 100% probability of being 0. In this case, after this Hadamard gate, we have something that is in the middle from 0 to 1. So when we say that, or some people said that a qubit is 1 and 0 at the same time, is something more complex. It's something that has a probability of being measured at 0 and the probability of being measured as 1. And we can work with these probabilities going up and down. And we also can work with these angles, and we can make calculations with interacting qubits ones with the other qubits. So the next property that is really more complicated to explain is the superposition, the the entanglement that is the property that really gets the bigger capability of the quantum computers. And using something like this that we call a C-NOT is a NOT gate controlled by this qubit. This gate makes flips the lower qubit if the top one is a 1 and does nothing if this is a 0. So when we see the possible states of this vector, we can see 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. So in this case, we have or both qubits are in the 0 position or both qubits are in the 1 position. Let's see. Can we plot this using this block sphere? We cannot do this anymore because these are no more independent random variables. They are entangled, and the result of measuring one of these is conditioning, or is both qubits are sharing some properties. So we cannot think in a quantum computer like a addition of different qubits, but a global state that is working in this big dimensional space. We sometimes create that kind of representations that tells that what are the possible accessible states of the system. And this is an intent of represent a high dimensional space that maybe is not so good. So what can we do with simulators, and why we use simulators for quantum computing? We always will like to use some simulators because it's the way we can debug our system. We cannot see inside the state vectors and these kind of things, but if we are doing a simulation, we can see them. So how we work with the circuit? Okay, we can use a simulator as a backend. We always try to create a system that works the same with simulators or with real computers. So we need to compile that we call transpile because it's transforming one circuit into one circuit. And what this step do is transforming our generic circuit to the specific qubits and gates that the computer can run. And then we run the circuit, get the results, and in this case, we can get what is doing this circuit. And what does the circuit do? We have an state that is a vector. So transforming the vector really is multiplying by a matrix. So what do these circuits do? Really make matrix multiplication in a native way. And you know that really big matrices, multiplying really big matrices is a hard problem. So we can use this capability of the system to make this big matrix multiplication. So really, we can calculate this matrix because we have a smaller circuit, but we cannot do this in a very big one. We can see the state, and we also can add measurements. And if we add measurements, we get this in the classical system, in the classical bits. And this is how it works in a real computer. So in this case, we have this state vector simulator that can simulate the execution. And how we get the results? We need to use shots. We need to run the state a lot of times and make an statistics of the measurements we get. Okay, so the quantum computer is deterministic, yes, when you make the same gates, you go to the same state, but you cannot see the state. You need to measure this, and to measure this, you need to measure different aspects of the circuit and get a statistic of what you have measured there. Okay, so think that the quantum state is a distribution of probability. You cannot measure this. You need to sample the distribution. And we can plot an histogram of what are the states. We know that we should have the same number here in the 0, 0 and in the 1, 1, because that's what we want to do with this circuit. We do not get the same results until we get infinite shots. And this is not error. This is sampling, okay? This is statistical. If we want to run this in a real computer, we can get the available backends, the different computers. We have real computers and simulators with big resources in the cloud. And we can find the less busy system. I have this executed because it could take some time in the queue. So when we execute, we get a job ID. We can monitor this job ID and get the results. And in this case, as you see here, you have the good results that we are expecting, the 0, 0 and the 1, 1. But we also have some results in other places of the circuit that we have nothing expecting here. Then these are related to errors. So what happened with the quantum system? We need to make algorithms that has sufficient difference between the results we are searching and the noise, so we can really identify what are the solutions of our circuit and what are not. So really the problem right now with the quantum computers is not the number of qubits, really is that as we have noise, if we make something with a big amount of qubits, it will need a lot of operations, and a lot of operations accumulate noise, and at the end, the noise equals the signal, and you cannot get nothing from the system, okay? So once you have the initial idea, I'm going really fast to show this, but okay, we can make machine learning using quantum computers, and let's see how we can do this. We have things like neural networks where we have different layers with weights that we can adjust and representation of values. We can create quantum circuits that makes these rotations of these vectors we saw in the initial place in some way that we can add some rotations for the weights, some rotations for the data, and get measurements at the end. And if this works like we expected, we can adjust some of these weights, some of these rotations, so the circuit can learn. And that's what we try to do here very quickly. So we really, let me go directly to the drawing that is easy to see. Okay. We can define a circuit. In this case, you remember that this created superposition, this created entanglement. So we have something with 4 qubits that are all entangled. And then we create rotations that depends on some parameters. So this is not a fixed circuit. It's a circuit that we can provide different angles here, and this will end up with some measurement. What is the good thing about quantum computers? That as these are rotations, this is a vector space that is big, but also is periodic. So as this is related to rotation and this is periodic, we can make the gradient, adding and subtracting some value to the parameters, and this is not finite. We do not add a small amount. We are doing this with a big angle, and this is not an approximation. Doing this with a big angle is the real gradient. So really, we can program something that we can say has an initial params that we set to these qubits, to these rotations. Forward is setting the parameters and running the circuit. And the backward is, okay, I need to add and subtract to each one of the qubits and run the circuit. So we can calculate the gradient. Our cost function in this case is, okay, I want any target that I want to get as a measurement, and I generate something that is just the difference from what we measure from the target. It is not really a machine learning system. It's just a proof that we can train this. And this way we can start running circuits and getting different values for these laws. Its iteration, it will change the value of the rotations, these rotations in the circuit, and make a measurement. And changing the rotations, we are adapting the value and getting better and better results until hopefully I get something. Okay, so we get our loss function is going down and our prediction is going to the 0.8 that I established as an objective. So really, we can use quantum computers to learn things in this classical quantum way. You see, we have used classical way of updating the parameters and the quantum system to run the calculations. If we can create a circuit that has this entanglement in a way that it can learn nonlinear relations in the data, we can have something that we can combine into a quantum classical hybrid neural network with classical layers that learn classical features and quantum layers that can learn this part of the information that the classical system cannot learn. So really, we have here an example of how we can use quantum computers for machine learning. Also, I think we are running out of time, so I think I can only show you the results of this. As we have a high dimensional space, you know that we can create support vector machines in a classical machine learning that is trying to find a separation from one class to other class. In classical support vector machine, we use a kernel trick that is transforming our data to a high dimensional space where we can separate in this high dimensional space. So what we can do with quantum computers? With quantum computers, we can access a very big amount of dimensions in this Hilbert, in this quantum space. So we can define a transformation, a mapping from our data points to points in this high dimensional quantum space. And as the support vector machine depends on the product of these vectors, we can make these products inside the quantum computer. So we can create some circuits, for this is data classification. We can create some circuit that we can run in the quantum computer, let me see, we can create a circuit with rotations, and we can put both elements in the quantum computer and make the multiplication of the vectors inside. No, we know that these multiplications are quick in the quantum computer. So we can get the matrix of the kernel using the quantum computer, provide this as a pre-compute kernel for a support vector machine, a classical support vector machine, and we can get a classification using this quantum kernel that can get some advantage in complex data for machine learning. I don't know if we have some time for questions. Sorry, I get to the end of the time.
And taking the same topic about the quantum computers, what is the limit? So this year IBM presented the 1000 qubit ones. How do you expect their market in 10 years at that point?
Really, I'm pretty sure that in 10 years we will be out in the new era of the quantum corrections, error corrections. So we will see really new ideas. I'm really excited with the next 5 years, where we will be enhancing the current NISQ computers to the limit where we can use them for things like machine learning in a useful way. So I'm really excited trying to get these computers that are being perfected for creating the quantum error correction. But in the meanwhile, we will be able to run pretty good circuits that could be useful for this kind of hybrid classical quantum machine learning, and maybe they can help to solve some difficult problems like predicting things in nature or in protein folding, these kind of things that we cannot do very well in classical systems.
Any other questions from the audience? So if not, before thanking again to the speaker, now we will go outside to take a group picture. We already prepared the roll-ups there. And now, let's thank to the speaker and see you at 2 o'clock.